Module 9, Lecture A, Model Export. By the end of this lecture, you will be able to describe the purpose and capabilities of torch.export in PyTorch 2.10.0. Export a trained nn.Module to an exported program suitable for deployment or further compilation, and inspect and validate exported models to ensure they produce consistent outputs with the original model. Core export concepts: eager versus exported. In PyTorch version 2.10.0, the torch export feature converts a model from eager execution, where it behaves like a regular Python object, into a static form. In eager mode, the forward method runs dynamically and lets you freely use Python features, which is convenient for development and experimentation. However, this flexibility is not ideal for deployment, especially outside Python or in environments that demand high performance and strict compatibility. Exporting the model creates a more stable and portable representation that is better suited for production systems, such as mobile applications or large-scale services. Torch export converts an eager PyTorch model into a static program that no longer depends on Python at runtime. It does this by tracing the model with example inputs and building a graph of operations that records inputs, outputs, and constraints. This graph is a structured representation that other tools can inspect and run, making the model more stable across different environments and versions. As a result, models developed interactively, such as recommendation models, can be exported and deployed in high-throughput systems without needing the original Python code. In PyTorch, eager mode lets you interactively run and debug your model, step through code, handle errors, and change structures, which is ideal for experimentation. When you export a model, it becomes more like a compiled artifact that is less flexible, but more predictable and portable. This exported form is better suited for stable deployment across different platforms. In practice, you usually develop and refine the model in eager mode, then export it once you are satisfied with its behavior. Python code: eager versus exported. This script demonstrates the difference between eager execution and exported style behavior using simple functions. It focuses on illustrating how static computation works conceptually, rather than exploring the internal details of the export system. The example may use basic numerical operations with a standard math library available if needed. Overall, the goal is to clarify the core ideas behind these two execution styles in a straightforward way. An eager square sum function takes a list of numbers and computes the sum of their squares. It starts with a running total set to 0, then goes through each number in the list and adds that number multiplied by itself to the total. After all numbers are processed, it returns the final total, which is the sum of all the squared values. This is called eager execution because each square and addition is computed immediately as the function runs. Exported square sum is a class that represents a computation with a fixed exported style structure and specific input requirements. Its constructor takes a length value that defines the required size of the input list it will process. This length is stored inside the object, so the class can later check that any given input matches this expected size. This design helps the computation behave predictably and handle inputs in a consistent way. This method, called run, takes a list of numbers and first checks that its length matches a required size stored in the object. If the lengths do not match, it raises an error to signal that the input is invalid. If the length is correct, it sets a running total to 0, then goes through each number in the list and adds its square to the total. In the end, it returns this total, which is the sum of the squares of all the input numbers. The print separator function is used to create a clear visual break in console output. It takes one input called title, which should be a text string. When the function runs, it prints a blank line, then 3 dashes, the title, and 3 more dashes. This produces a formatted separator line that helps distinguish different sections when viewing the program's output. We begin by defining a fixed list of input values, 1.0, 2.0, and 3.0. This list is deterministic, meaning it is predefined rather than randomly generated, so it produces the same results every time the code runs. These values serve as consistent test inputs for both the eager computation and the exported computation used later in the script. Before using the input list, the program first checks whether its length is 0 or less to make sure it is not empty. An empty list would cause problems in later calculations, so this validation step protects the code from runtime errors. If the list is empty, the program raises a value error with a clear message that the input list must not be empty. This ensures the program only continues when it has valid data to work with. We now run the eager style computation by calling the function that computes the sum of squares for the input list. This function goes through each element, squares it, and adds it to a running total. The final total from this process is stored in a variable called the eager result. This eager result will later be compared with the result produced by the exported style approach. We create an instance of the exported square sum class to work with input data of a fixed length. By giving the constructor the length of the input list, we make sure the exported program is built to accept only inputs of that exact size. This strict size requirement is essential for the exported style and contrasts with the more flexible eager style, which can handle inputs of varying lengths. As a result, the exported version enforces consistent input dimensions every time it is used. To run the exported style computation, we call the program's run method with the input values. This method first checks that the number of inputs matches the expected size defined when the program was created. If the sizes match, it then computes the sum of the squares of the input values, just like in the eager execution approach. This shows that the exported style both enforces input constraints and performs the same underlying calculation. We now verify that the eager and exported approaches produce the same numeric result. After marking this section in the console and briefly reminding ourselves of the input values, we show the output from the eager style computation. We then show the output from the exported style computation, which uses the exported class. Comparing these two outputs confirms that both methods yield identical results for the same input data. This example shows that the exported program requires its input to have a fixed length. We create a short input list with only two values, 1.0 and 2.0. Because this list is shorter than the expected size, it lets us observe how the program reacts when the input length does not match what it was designed to handle. The focus is on demonstrating this mismatch in input size and its effect on the program's behavior. We test the exported program with an input list that has the wrong length to show how it handles incorrect input sizes. After printing a separator line that labels this test, we run the program inside a try block using a shorter list than expected. Because the input length does not match the required size, the program raises a value error. We catch this error and print a message explaining that the exported program failed and include the error details. This demonstrates that the exported style program strictly enforces the expected input length. We test the eager square sum function with a shorter input list to show that it works for inputs of any length. This confirms that the eager approach is flexible and does not require a fixed size for the data it processes. In contrast, the exported style needs inputs of a predetermined length. This comparison highlights that the eager style is more adaptable when handling varying input sizes. This script compares eager computation with an exported style using a simple example that sums the squares of a list of numbers. In the eager version, a function directly computes the result for any list length. In the exported style, a class expects the list to have a fixed, predefined length and raises an error if the input length does not match. For the original list of numbers, both approaches give the same result, showing they are equivalent in that case. However, when a shorter list is used, only the eager function works, while the exported style fails, illustrating that eager computation is more flexible, whereas the exported style strictly enforces input constraints. Graph capture constraints. When you export a model in modern deep learning frameworks, you are turning its behavior into a static computation graph rather than arbitrary Python code. This process must follow graph capture constraints, which restrict the kinds of operations and control flow that can be represented. Unlike in a fully Python-driven setting, the export system needs computations that can be traced and analyzed without relying on Python at runtime. Only certain Python patterns and tensor operations are allowed, and they must support static analysis. Understanding these limits is essential for designing models that can be reliably optimized and deployed. For graph capture to work, the control flow and tensor shapes must be predictable or symbolically representable. If loop counts or conditions depend on changing Python data structures or random logic at runtime, the exporter cannot build a reliable static graph. In contrast, when these behaviors depend on tensor values or symbolic dimensions, the exporter can still handle variable length data. This is especially important for models like recommendation systems or language models, where hiding variability in Python logic can cause export to fail or produce graphs that do not generalize. When exporting models, only pure tensor operations, such as linear layers and convolutions, are reliably captured because they have well-defined behavior. Side effects like writing to files, logging, or interacting with hardware cannot be represented in a static computation graph. So models that perform these actions directly in their forward pass will not export cleanly. To make such models exportable, you should separate the numerical computations from any side effect code and handle those side effects externally. This separation makes models easier to export, run on different platforms, and maintain performance and correctness in production. Python code. Graph capture constraints. This script demonstrates the basic constraints of graph capture by comparing export-friendly and export-unfriendly model behavior. It highlights how certain patterns work well with graph export, while others cause problems. The main focus is on keeping control flow predictable and managing side effects carefully so that models can be captured and exported reliably. This script is designed to run using only Python standard libraries, so you do not need to install any extra packages. A commented line mentions installing PyTorch, but it is not active and PyTorch is not actually used. As a result, the code stays simple, lightweight, and easy to execute without managing external dependencies. We begin by importing the random module to add unpredictability to the program, which helps show how changing control flow can alter the code's behavior. We also import the operating system module, which is commonly used to work with environment settings and file paths. In this script, it is not used directly yet, but it is included in case we later need it to help configure the program's environment. We begin by setting a fixed seed for the random number generator, so that any random behavior in the script is reproducible, which is important for consistent debugging and testing. Then we create a simple list with the values 1, 2, and 3 to act like a small tensor. This basic structure lets us demonstrate tensor-style operations in a clear way without relying on more complex tensor libraries, keeping the focus on the core computation logic. A pure computation function takes a list of tensor values and a scale, multiplies each value by the scale, and collects the results in a new list. It processes each input value in turn, applies the scaling, and appends the scaled value to this result list. At the end, it returns the new list of scaled values. Because it only uses its inputs and does not change anything outside the function, it has no side effects. This example defines a function that both changes external state and behaves randomly. It treats a tensor variable as global, so the function can modify it directly. Inside the function, a random choice decides whether to append the value 99 to this tensor, making the control flow unpredictable. The function then returns the original list of tensor values, which does not clearly correspond to the random modification of the global state. We choose a scale factor of 2 to multiply each element in a small tensor-like list, setting up a simple and predictable computation. We then call a pure computation function that takes this list and the scale factor and returns a new list where every element has been scaled. Because this function only performs calculations and has no side effects, its control flow is predictable. This makes it export-friendly and suitable for graph capture in machine learning frameworks. In this example, we show behavior that is unpredictable and not suitable for exporting. A function with side effects is called on a small tensor and can alter a global version of that tensor. Because it introduces randomness and changes global state, the resulting control flow becomes unpredictable. This makes the computation unreliable for situations where consistent, repeatable behavior is required. We begin by showing the initial values of the small tensor, which are 1, 2, and 3, to establish a clear starting point before any changes are made. We then print the result of a pure computation function that processes this tensor. This function uses a fixed loop and multiplies each element by a constant factor, so its output is stable, predictable, and free of side effects, or randomness. We first show the current state of the small tensor after it may have been modified by the side effect computation, highlighting that the global state can change in unexpected ways. Then, we display the output returned by the side effect function, which still reflects the original tensor values. This contrast demonstrates that even though the function returns familiar data, it may have altered other parts of the program, leading to behavior that is not clear or predictable. The first print statement explains that the pure computation path is suitable for export because it uses fixed loops and has no side effects, so its behavior is predictable and does not change any external state. This makes it reliable when consistent output is required, such as when exporting models. In contrast, the second print statement shows that the side effect path is problematic for graph capture because it changes global variables and uses randomness. These changes introduce unpredictability, which makes it difficult to capture a stable computation graph for exporting or optimization. The code prints the length of the result produced by the pure computation function to confirm that its output shape is consistent and predictable. This check helps ensure the function behaves in a way that is suitable for export. By verifying the length, we confirm that the pure computation path keeps its expected structure and is not affected by side effects or randomness. This script compares two kinds of computations on a small list of numbers. The first is a pure computation that scales each element in a predictable way, does not change anything outside the function, and does not use randomness, so it always produces the same scaled list and is safe to export or capture in a computation graph. The second introduces side effects by possibly modifying the original list and using random branching, so its results can differ from one run to another and are not suitable for export. When you run the script, you see the original list, the stable output from the pure computation, and then the possibly changed list after the side effect computation. The key point is that pure side effect-free code with fixed loops is reliable for exporting, while code that mutates global state and uses randomness is not. Supported export patterns. Supported export patterns describe which models and usage styles can be reliably turned into an exported program. The system is built to handle common deep learning architectures such as feed-forward, convolutional, recurrent, and attention-based models, as well as custom designs that use standard building blocks. In general, if the model's forward pass is a sequence of tensor operations that PyTorch can trace, it can usually be exported. This remains true even when the model includes control flow, like conditionals and loops driven by tensor values. So dynamic behaviors, such as branching in a vision model or iterative processing in a sequence model, can still be captured in a single deployable graph. Export systems allow a single model to handle dynamic shapes and flexible inputs, which is important for tasks like speech recognition and recommendation where input sizes vary. Instead of building separate models for each input configuration, you can export one program that adapts at runtime within defined limits. This makes it possible to serve many different request patterns efficiently while using less memory and maintaining one optimized model. Model exporting can support complex deployments, not just single standalone models. You can build pipelines where one model extracts features from sensor data and another uses those features for predictions, even across different devices. The exporter can also include pre-processing and post-processing steps, such as normalization and tokenization, as long as they use supported operations. This integrated approach reduces mismatches between training and serving, and makes it easier to move models from experimentation into production. By understanding these patterns, you can design models that are naturally exportable and smoother to deploy. Python code, supported export patterns. This script gives a simple overview of which export patterns are supported. It uses a conceptual simulation instead of real PyTorch code, so the focus stays on the ideas rather than implementation details. The main goal is to illustrate how export can handle different kinds of control flow. It also highlights how dynamic shapes are treated at a high level, without going into low-level framework specifics. This part of the code is a placeholder reminding the user to install external libraries needed for machine learning, such as PyTorch, Torch Vision, and Torch Audio. It shows a typical installation command that would prepare the Python environment so the script can run correctly. The command is commented out, meaning it doesn't run automatically and instead serves as an instruction for the user to perform the installation manually, if required. We begin by importing 3 standard Python modules to prepare our script. The math module provides common mathematical functions and constants. The random module lets us generate random numbers, which can help with tasks like initializing model weights or creating test data. The OS module enables interaction with the operating system, such as handling files and directories. Together, these imports set up the tools needed for numerical work and basic system operations in the program. We set the random seed to 0, so that any random numbers generated by the code follow the same sequence every time it runs. This makes the behavior of random operations predictable instead of changing from run to run. As a result, experiments or simulations can be repeated with identical outcomes. This reproducibility is important for testing, debugging, and comparing results reliably. This simple feed-forward function takes a list of numbers and transforms each one in the same way. For every input value, it multiplies the number by 2 and then adds 1. The output is a new list where each element has been changed by this linear transformation. This mirrors what happens in a basic neural network layer, where inputs are adjusted by weights and biases to produce outputs. The function branching model takes a list of numbers and a threshold, then first computes the average of the list. If this average is greater than the threshold, it applies the simple feed-forward transformation twice, creating a stronger change to the data. If the average is not greater than the threshold, it applies the simple feed-forward transformation only once. In this way, the model adjusts how intensely it processes the data based on the characteristics of the input. This function processes a list of values step by step and produces a new list of results. It starts with an empty results list and a counter set to the first position. As long as the counter is within both the allowed number of steps and the length of the input list, it takes the current value, divides it by 2, and adds the result to the outputs. After each value is processed, the counter moves to the next position. When the loop finishes, the function returns the list of halved values. The dynamic shape pipeline function is built to handle lists of different lengths by first checking that the input is a valid, non-empty list and raising an error if it is not. It then runs the list through a branching model that applies different transformations depending on whether the list's average value is above or below a given threshold. The result is passed to a loop sequence model, which processes the list step by step up to a specified maximum number of steps. Finally, it returns the processed list, providing flexible handling of inputs with dynamic shapes. The feature extractor function normalizes a list of raw values using min-max scaling. It first finds the smallest and largest values in the list. If they are the same, meaning there is no variation, it returns a list of zeros of the same length. Otherwise, it subtracts the minimum from each value and divides by the difference between the maximum and minimum. This converts all values to a range between 0 and 1, making the data easier to use in later processing steps. The prediction head function takes a list of features and a bias value, adds all the feature values together, then adds the bias to get a single score. This score is a simple linear combination of the inputs plus a constant. The function then compares the score to a threshold of 1.5. If the score is greater than this threshold, it outputs 1 to indicate a positive decision. Otherwise, it outputs 0 for a negative decision. This thresholding step converts a continuous score into a binary classification outcome. The two-stage pipeline function processes data in 3 main steps. It first uses a feature extractor to turn raw input values into normalized features that are easier to work with. It then runs these features through a dynamic shape pipeline that uses branching and looping models to handle the data according to conditions like a threshold and a maximum number of steps. Finally, a prediction head computes a score and compares it to a threshold to produce a binary decision. The function outputs this decision along with the extracted features and the processed data for further use. We create 2 lists of numbers to test how the pipeline handles inputs of different lengths. The short example has 3 values, 0.2, 0.4, and 0.6, representing a shorter input sequence. The long example has 5 values, 0.1, 0.3, 0.5, 0.7, and 0.9, representing a longer sequence. By comparing how the pipeline processes these 2 lists, we can see that it supports dynamic input shapes. We run the 2-stage pipeline on a short example list using 4 key parameters: the list itself, a threshold, a maximum number of steps, and a bias. The threshold is set to 0.4 to control how the pipeline branches, and the maximum of 5 steps limits how many iterations the loop model can perform. The bias is set to 0.1 to slightly shift the final prediction. The function returns three outputs: a decision, extracted features, and a processed version of the input, which we store for analysis. This setup lets us see how the pipeline behaves on a simple input under these specific settings. We now run the two-stage pipeline on a longer example list using four main settings: the input list itself, a threshold of 0.3 that controls how the pipeline branches, a maximum of 3 steps that limits how many times the loop can run, and a bias of 0.2 that adjusts the final prediction. This pipeline processes the input through its dynamic shape logic and prediction head. It then returns 3 outputs: the final decision, the features extracted from the input, and the processed version of the list after the pipeline has been applied. These 3 results are stored for later use as the decision, the features, and the processed output for the long example. This line simply prints a placeholder message where PyTorch version information would normally appear. In this script, it is not actually using the PyTorch library, but symbolically represents the idea of exporting models or scripts. Its main purpose is to remind you where such version details might matter in a real project that does involve PyTorch. This line prints a message to show that the same processing pipeline is used even when the input size changes. It reports the length of a short example input list and the resulting decision from the pipeline. This highlights that the pipeline can flexibly handle different input lengths while keeping its processing logic consistent. This line reports how many elements are in the process list for the short dynamic example. It calls a built-in function to measure the length of the list produced by the dynamic shape pipeline. By checking this length, you can see how the pipeline handles an input of shorter size. This helps confirm that the pipeline correctly processes inputs of different lengths. This line prints a message to show that the longer input list is processed using the same computation pattern as the shorter one. It reports the length of the longer list and the decision produced by the pipeline. This confirms that the pipeline can handle inputs of different sizes while keeping its processing logic consistent. This line reports how many elements are in the processed output produced from a long input. It uses a length operation to measure the size of the processed list that comes out of the dynamic shape pipeline. By checking this value, you can confirm that the pipeline handles inputs of different lengths in a consistent way. This demonstrates that the processing model is flexible and robust when dealing with variable size data. To check how the model branches, we compute the average of the features from a short input example. We do this by adding all the feature values and dividing by the total number of features. The resulting average is then printed to show how the model has transformed the input data. This average value is important because it helps determine the branching behavior inside the model. This script builds a simple, PyTorch-free simulation of a machine learning pipeline that processes lists of numbers with dynamic behavior. It defines a basic feed-forward style transformation and a branching step that applies this transformation once or twice depending on whether the input average exceeds a threshold. A loop-based model then further processes the data for a limited number of steps, and a feature extraction stage normalizes the values using min-max scaling. A prediction head converts these features into a score and applies a threshold to produce a binary decision. 2 example lists of different lengths are run through the full pipeline, and the outputs show how it adapts to varying input sizes while keeping a consistent processing pattern, including confirmation of the branching behavior through the average of the short example's features. Exporting models with torch.export. Defining example inputs. When exporting a trained neural network, you must provide example inputs that closely match the real data the model will see in production. These examples need to have the same shapes, data types, and structure as the deployed system expects. The export process uses them to trace how data flows through the network and to build a portable computation model. If the examples are unrealistic, the exported model can be incomplete or invalid, such as when an image classifier is exported with single grayscale images instead of batched color images. When preparing example inputs for exporting a model, you should match the variability and structure of the real deployment environment. Many models handle multiple inputs or inputs of different sizes, so you must decide which dimensions are fixed and which can change, and set up the export to support that. For speech recognition, this means using a representative audio waveform and attention mask that reflect production data. For recommendation systems, it means including user and item feature vectors and interaction histories as they will appear in production. This alignment ensures the exported model can correctly handle real-world data flows. When defining example inputs for exporting a model, you should choose cases that reflect real operational limits and edge conditions, because these choices affect performance and tool compatibility. If the model will run on hardware with tight memory, use examples that match the maximum expected load. In high-stakes areas like medical imaging or autonomous driving, include especially challenging scenarios to expose potential problems early. Well-designed example inputs can reveal hidden dependencies or control paths before deployment, leading to more reliable integration into real-world systems. Python code, defining example inputs. This script defines some example inputs and uses TensorFlow to imitate how a model would behave with them. The main goal is not to train a real model, but to check that the shapes of the inputs and outputs are correct. By running these simple consistency checks, you can confirm that the data flows through the model structure as expected before moving on to more complex tasks. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. Using this exact version helps ensure the code behaves as expected, since different TensorFlow versions can change features or introduce bugs. This command is usually run in a terminal or in a Jupyter Notebook cell to prepare the environment before running the rest of the script. We start by importing 3 key Python libraries. The operating system library lets us interact with the system for tasks like working with files and environment settings. The random module allows us to generate random numbers, which is useful for creating random data or initializing values. Finally, the numerical computing library NumPy helps us efficiently work with arrays and perform mathematical operations on them. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers component from Keras, which provides the basic building blocks for designing a network structure. Together, these imports give us the essential tools to define and train neural network models efficiently. We begin by setting a seed value of 42 so that any random operations in our code give the same results every time. To achieve this, we set the seed for the random library, then for the NumPy random number generator, and finally for TensorFlow's random operations. Using the same seed across these libraries ensures our experiments are reproducible and their results consistent. This line of code displays the version of TensorFlow currently in use. It provides a quick check that the environment is running the expected TensorFlow version. Confirming the version helps ensure that the rest of the code will be compatible and behave as intended. We build a tiny image classifier by defining a Keras model that takes 28 by 28 grayscale images as input. We first apply a 2-dimensional convolutional layer with 4 small filters and a ReLU activation to extract basic features. The result is then flattened into a one-dimensional array so it can be passed to a dense layer. Finally, a dense layer with 10 units and a softmax activation produces a probability distribution over 10 possible classes. The model is compiled using the Atom optimizer, which is commonly chosen because it trains neural networks efficiently and adapts well during learning. The loss function is sparse categorical cross-entropy, which is appropriate for classification problems where the target labels are given as integers. Together, these choices define how the model updates its weights and how its performance is measured during training. We begin by creating a small batch of example input images for the model, with a batch size of 2 so that we generate 2 images. Each image is 28 pixels high and 28 pixels wide with a single channel, matching the format of typical grayscale images. We use a numerical library to fill these images with random values that have the correct shape. Finally, we convert the data to the float32 format, which is a standard choice for image data in machine learning and ensures it works smoothly with TensorFlow operations. The code first prints the shape of the batch of example images to confirm that the input dimensions match what the model expects. It then prints the data type of these images to verify that the numerical format is correct. Together, these checks ensure the input data is properly structured and formatted so the model can process it accurately. The model is run once, using the example images as input to generate predictions. This is done with the Keras prediction function, which feeds the input data through the trained model and returns the predicted outputs. A silent mode setting is used so that the prediction process does not print any extra information to the console, keeping the execution clean and focused on the results. In this step, we check that the shape of the model's output batch matches what we expect. By printing the shape of some example predictions, we can confirm that the outputs are structured correctly. This means the number of outputs and their dimensions line up with the classes or categories the model is supposed to predict. Verifying this helps ensure the model is producing predictions in the right format before we move on to further evaluation or use. We now look at the model's prediction output and check the length of the first prediction vector. This length tells us how many classes the model is predicting. In this example, the length is 10, which matches the 10 categories in our classification task. Verifying this confirms that the model's output shape is consistent with what we expect for the problem we are solving. In this example, we deliberately create an input array with the wrong shape to demonstrate error handling. Using a numerical library, we generate random data that matches the batch size, height, and width, but we leave out the channel dimension and convert the result to a float32 type. This produces an input that does not match the model's expected shape. We then use this mismatched input to intentionally trigger an error when it is passed to the model for prediction. We deliberately call the model with input data that has the wrong shape and place this call inside a try block so we can handle any errors cleanly. Because the input dimensions do not match what the model expects, it raises an exception. The exception is then caught, and we print the type or class name of the error. This lets us see exactly what went wrong without stopping or crashing the entire program. This script shows how to build a simple image classification model in TensorFlow using a small convolutional neural network for grayscale images that are 28 by 28 pixels. It fixes random seeds for reproducibility, then defines a network with a convolutional layer, a flattening step, and a final dense layer with softmax activation to classify images into 10 categories, compiled with the Atom optimizer and sparse categorical cross-entropy loss. The script creates a small batch of random example images, checks their shape and data type, and runs them through the model to verify that the output predictions have the expected shape. It then deliberately feeds input with the wrong shape to trigger an error, illustrating that the model requires consistent input dimensions, and printing the error type to emphasize this point. Exporting neural networks. After training a neural network and preparing example inputs, the next step is to export it into a stable form for deployment. This means freezing its structure and behavior and removing reliance on dynamic training features such as Python control flow. During export, the system traces the model's forward pass to record the operations and data flow as a static, device-independent graph. This exported graph can then be optimized and run without Python, which is essential for reliable, high-performance deployment in production environments like mobile apps and embedded devices. When exporting a neural network, the system separates it into a computation graph and a set of parameters. The computation graph describes the sequence of operations that turn inputs into outputs, including any branching or reshaping seen during example runs. The parameters, such as weights and biases, are stored as fixed tensors that plug into this graph but do not change its structure. This separation lets you reuse the same graph with different parameter sets, so a base model can be fine-tuned for different clients or regions simply by swapping parameters without redesigning the computation itself. When exporting neural networks, the aim is to produce a model artifact that other systems can reliably use even when they have stricter constraints than the training setup. This often involves adapting the model to work with specific hardware accelerators or inference engines that require certain operations or fixed input shapes. The export process captures and simplifies the model's behavior, so it is easier to analyze and optimize, sometimes turning dynamic behavior into more static patterns. Overall, exporting is both a technical and design task that ensures the model is robust and portable across different deployment environments, from cloud services to low-power devices. Python code, exporting neural networks. This script demonstrates a very small neural network export example. Instead of focusing on training with large datasets, it simply shows how to save the network's weights and a description of its structure. The goal is to illustrate the basic concept of exporting a model in a clear and lightweight way. For this example, you do not need to install any extra libraries. The script runs using only standard Python libraries or ones that are already available in most Python setups. This makes it easy to use and widely accessible without additional configuration or dependencies. We begin by importing the numerical computing library NumPy so we can work efficiently with arrays and perform mathematical operations. We also import Python's built-in random module, but give it a different name to keep it distinct from NumPy's own random tools. This setup lets us clearly separate the two sources of randomness and use them in a controlled way. It is important for keeping our data generation and experiments reproducible and consistent. In this script, we use TensorFlow as the main framework for building and managing our neural network. It provides tools to define a simple model, compile it, and run the training process. TensorFlow also makes it straightforward to export and reload model parameters, which helps keep our experiments consistent and reproducible. We set fixed random seeds using tools like the random module and numerical libraries so that any random numbers generated are the same every time the code runs. This makes the program's behavior predictable and repeatable. Reproducibility is important because it allows us to consistently reproduce results, making debugging easier and helping us verify that the code works as intended. Setting the TensorFlow random seed makes random operations in your code produce the same results every time you run it. This consistency is called reproducibility. It is important because it lets you reliably compare experiments and debug behavior when developing and testing machine learning models. We begin by printing the TensorFlow version being used, which helps us understand the exact environment in which the code is running. This information is important for checking compatibility, since different versions can change features or behavior. It is also useful when debugging or sharing code with others, so everyone can reproduce the same setup and results. We begin by creating a simple synthetic dataset to demonstrate the process. Using a numerical library, we generate 8 evenly spaced floating point numbers between -1 and 1. This sequence serves as a basic input for our neural network model. The goal is to keep the data straightforward so we can focus on how to export and reload the model rather than on handling complex datasets. We reshape the input data so it matches the expected input format for the dense layer in our neural network. This means converting a one-dimensional array into a two-dimensional array with a single column. Doing this ensures the data has the correct shape the model requires. It is a necessary step for the network to properly handle the inputs during both training and prediction. We create random noise using a normal distribution with a mean of 0 and a small standard deviation of 0.05. Matching the size of our input data. This noise is added to the synthetic target values to introduce slight randomness. By doing this, we simulate the natural variability found in real-world data while keeping the overall signal mostly unchanged. We are creating target values for training a neural network by applying a simple linear rule. Each input value is multiplied by 2. To make the data more realistic, we then add a small amount of random noise. This noise comes from a normal distribution and is converted to the same numeric type as the inputs. Adding this variability helps simulate real-world measurements, which are rarely perfectly exact. We define a very small neural network using TensorFlow's sequential API to illustrate how a model is set up. It has a single input layer that takes data with one feature, followed by a dense layer with one unit. This dense layer has no activation function, so it performs only a simple linear transformation on the input. The goal of this design is not complex behavior, but to clearly demonstrate the basic structure of a neural network model. Before training, the model is compiled by choosing an optimizer and a loss function. In this case, the optimizer is stochastic gradient descent, a common method that updates the model's parameters to reduce error. The loss function is mean squared error, which calculates the average of the squared differences between predicted and actual values. This combination is well suited for regression problems where the goal is to predict continuous numerical outputs. The model is trained using the fit method, which adjusts its parameters to reduce the difference between its predictions and the actual target values. This training runs for 50 epochs, meaning the model processes the entire dataset 50 times to refine its weights. During this process, the verbose setting is turned off so that training logs are suppressed and the console output remains clean and focused only on essential information. We run the trained model on the input data to generate a set of reference predictions. This uses the model's prediction function, which processes the data through the network to produce outputs. Detailed logging is turned off, so the process stays focused on the results. These reference outputs are then used later to compare with predictions from a reloaded version of the model, helping verify that the export and import steps are consistent. We validate the shapes of the model outputs against the target data to ensure they match. This check confirms that the model's predictions are structured correctly before we export anything. By asserting that the shapes are equal, we prevent mismatches that could cause errors during the export process. This simple validation step helps keep the workflow reliable and consistent. We create a dictionary to describe the structure of a neural network, so we can export and later reconstruct its architecture. First, We record the model's input shape by converting it to a list and removing the batch size dimension. We do the same for the output shape, keeping only the meaningful dimensions. Finally, we describe the model's layers, which in this example consist of a single dense layer with one unit and a linear, or no, activation function. We extract the trained weights and biases from the dense layer to capture the model's learned parameters after training. The weights describe how neurons are connected, and the biases shift the outputs produced by those connections. By retrieving and saving these values, we preserve the model's learned state so it can be replicated, reused, or analyzed later. The code converts the neural network layer's weights into a list so they can be easily saved and shared. Lists work well with JSON, a common format for exporting data in a structured, readable way. By turning the weights into a list, we make them compatible with JSON serialization and ensure they can be reliably stored and transferred between different systems of applications. The biases from the neural network's dense layer are converted into a simple list so they can be easily saved in a format that works with JSON. This step makes the biases straightforward to serialize and store. It also helps ensure the model's parameters are exported in a consistent and easy-to-handle way. We are creating an export artifact, which is a single package that stores both the structure and the learned parameters of our neural network. It combines the model description we defined earlier with the trained weights and biases. The structure is saved in a dictionary entry labeled as the model structure, and the weights and biases are converted to lists and stored under their own entries so they can be easily serialized. This artifact lets us save, reload, or share the complete model configuration and parameters in a convenient format. We rebuild the neural network by using the previously exported description of its structure. With TensorFlow, we create a new sequential model and define the input layer so that its shape matches the original model's input dimensions. We then add a dense layer with a single unit and no activation function, mirroring the original configuration. This recreates the same architecture as before, so the exported weights and biases can be loaded back into the model correctly. We load the trained parameters into the first layer of the reloaded model by setting its weights and biases from the exported values. To do this, we convert the exported weights to a float32 NumPy array, and we apply the same conversion to the biases. Using these converted arrays ensures the reloaded model has exactly the same learned parameters as the original, so it produces consistent outputs. Next, we run the reloaded model on the same inputs as before, so we can compare its outputs with those of the original model. This comparison step is essential to confirm that the model behaves the same way after being exported and loaded again. We use the predict function from TensorFlow to generate the outputs, and we suppress extra logging so the results are clean and easy to compare. To check that the original and reloaded models are consistent, we compare their outputs by computing the maximum absolute difference between them. We first take the absolute difference for each pair of corresponding output values, then find the largest of these differences. If this maximum difference is effectively 0 or extremely small, it shows that the reloaded model behaves the same as the original. This confirms that the export and reload process preserve the model's behavior accurately. We first check the shape of the original model outputs to confirm the dimensions of the data it produces. Then we compare this with the shape of the outputs from the reloaded model to ensure they match. Next, we compute the maximum absolute difference between the original and reloaded outputs to verify that the reloaded model behaves the same as the original, confirming that the export and reload process worked correctly. Finally, we print a description of the export structure, which summarizes the model's architecture including its input and output shapes and layer details, to make the model's structure clear and reproducible. This script shows how to export and reload a simple neural network model in TensorFlow. It creates a small synthetic dataset where inputs between -1 and 1 are mapped to targets that are roughly double the inputs with added noise. Then trains a basic one-layer network using mean-squared error. After training, it exports the model's structure and weights into a dictionary, rebuilds a new model from this exported data, and compares the outputs of the original and reconstructed models. By checking that the output shapes match and that the maximum absolute difference between the two sets of predictions is negligible, and by printing the TensorFlow version and model description, the script confirms that the export and reload process works correctly. Persisting exported models. After exporting a model, the next step is to save it as a stable artifact that can be reused and shared. This means converting the in-memory model into a stored form, such as a file or an object in a storage service, so it can be versioned and reliably reloaded later. Doing this allows teams to move models between different environments without needing the original training setup. For example, a data science team can export a recommendation model and hand it off to an engineering team for deployment, keeping development and production consistent even if the training resources change. When you save exported models, you need a clear system to organize and track them over the life of a project. You will often have many versions, trained in different ways or for different purposes, so consistent naming, metadata, and versioning are essential. This helps teams quickly see which model came from which experiment or deployment, such as tagging by training date and data cohort. Good organization is especially important for debugging and compliance because it lets you trace, inspect, and explain the exact model used when problems appear in production. Persisting exported models create stable artifacts that can be deployed across different platforms and environments. Once saved, these models can move between systems with different operating systems or hardware, and can be optimized without needing the original Python code. This portability supports consistent use of the same model, such as a risk model used both in the cloud and on premises, and makes collaboration easier when partners use different software stacks. Overall, persisted models act as a common format for model logic and help streamline the path from research to production. Python code, persisting exported models. This script demonstrates how to persist exported style models by simulating an export process with a simple TensorFlow saved model. The main goal is to show how models are saved and later loaded again. It also emphasizes validating the model's outputs after loading to ensure they match the expected behavior. Overall, the focus is on the complete cycle of exporting, restoring, and checking the correctness of style models. A line that begins with an exclamation mark is a shell command used to install TensorFlow version 2.20.0, not a line of Python code. It makes sure that this exact version of TensorFlow is available before the script runs. This matters because different TensorFlow versions can change features and behavior, which can affect how the code works and whether it runs correctly. We start by importing 3 key Python modules to prepare our script. The operating system module lets us work with files and directories. The path handling module provides a more intuitive, object-based way to manage file system paths. The random module allows us to generate random numbers, which is useful for setting seeds or creating test data. Together, these imports set up tools for managing files, paths, and randomness in our program. We start by importing NumPy, a widely used Python library for numerical work. This gives us access to efficient tools for working with arrays and matrices. These capabilities are essential for the numerical computations and data manipulation tasks we will perform later in the script. Here, we import TensorFlow, a widely used framework for building and training machine learning models. In this context, it serves as a lightweight model framework that provides tools to define, train, and export models efficiently. This import is essential because it gives us access to TensorFlow's large collection of built-in functions and classes, which greatly simplify working with neural networks and other machine learning tasks. We set a seed value, such as 42, to make random operations reproducible, so they give the same results every time the code runs. We apply this seed to the standard random module, to the NumPy random number generator, and to TensorFlow's random number generator. This controls randomness in things like generated numbers and initialized model weights. By doing this, we create a consistent, controlled environment where experiments can be reliably repeated. This line checks and prints the version of TensorFlow that is currently in use. It provides a quick way to verify that the environment is using the expected version of the library. Confirming the version is important because it helps ensure that the rest of the code will be compatible and run as intended. We define a simple neural network using the Keras sequential API, which stacks layers one after another. The model begins with an input layer that takes data with 4 features. It then passes this input to a dense layer with 3 neurons that use the ReLU activation function to add nonlinearity. Finally, the network ends with a dense layer that has a single neuron with a linear activation, which is standard for regression tasks. Overall, this creates a basic feed-forward neural network suitable for demonstration. Before training, the model is compiled, which means setting up how it will learn and how its performance will be evaluated. In this case, the Atom optimizer is used because it is efficient and works well with sparse gradients. The loss function is chosen to be mean squared error, which is appropriate for regression problems where we want to reduce the average squared difference between predictions and actual values. With this configuration, the model is prepared to learn effectively from the training data. We create a small, deterministic batch of training data using a 2-dimensional input array with one example that has 4 features, with values 0.1, 0.2, 0.3, and 0.4. The corresponding target output is another 2-dimensional array with one example containing the single value 0.5. This setup defines one input example and its expected output. Using deterministic data like this makes the training process reproducible and consistent across different runs. Before training the model, we first verify that the input and output data have shapes that match the model's layers. We check that the training input is arranged as one row with 4 values, consistent with the 4 inputs expected by the model. We also confirm that the training output is one row with a single value, matching the model's single output. These checks help catch shape mismatches early and prevent errors during training. The model is trained using a fit method that adjusts its parameters to reduce the loss function. In this example, the training data contains just one input and one output. The model is trained for 10 epochs, meaning it goes through this small dataset 10 times. The verbose setting is turned off so that no training progress messages are printed, keeping the console output minimal. We create a small test input using a 2-dimensional NumPy array with 1 row and 4 columns, containing the values 0.9, 0.8, 0.1, and 0.2 as 32-bit floating point numbers. This array serves as a simple example to verify that the model's export process works correctly. After saving and reloading the model, we can use this input to confirm that the model still handles and processes the data as expected. Before using the model to make predictions, we first check that the sample input has the correct shape. Specifically, it must be a two-dimensional array with 1 row and 4 columns. This validation step is important because the model is designed to work only with inputs of this exact form. Ensuring the correct shape helps prevent errors and makes the inference process run smoothly. We use the model's prediction function to generate an output from a sample input, and this serves as our reference result. This step is important because it captures how the original model behaves before we save it. After we save and reload the model, we compare the new output to this reference. If the two outputs match, we can be confident that the saved and reloaded model is consistent and accurate. We first display the prediction produced by the original model so we can use it as a baseline for later comparisons. To make this output easier to read and compare with future results, we convert it into a single one-dimensional array. This flattened format helps us quickly see and evaluate differences between the original prediction and any updated model outputs. We begin by defining a directory where the exported model will be saved, using a path object created with the pathlib library. This directory, named for the exported model, will serve as the destination for storing the model in a stable, consistent format. Saving the model here preserves its state so it can be reused, shared, or deployed later without needing to retrain it. Before saving the model, the code makes sure the export directory is clean. It first checks whether the directory already exists, and if it does, it goes through each item inside. Any files it finds are deleted so that no old data can interfere with the new model export. Items that are not files, such as subdirectories, are skipped and left unchanged. The code saves the trained model as a TensorFlow saved model, exporting it to a chosen directory so it can be reused or deployed in other environments. In this format, the model's architecture and learned weights are stored together, ensuring nothing essential is lost. This saving step is important for keeping the model available over time and for easily sharing it with others or moving it into production. After saving the model, the code checks whether the folder where it was stored actually exists. It does this by calling a method that tests the export directory path. If the folder is found, the program prints a confirmation message. This simple check helps verify that the model was successfully saved in the intended location. To simulate a real deployment environment, the code reloads the saved model into memory, using a TensorFlow layer that points to the export directory. This layer is set up to use the default serving endpoint, so the model can run inference as it would in production. Doing this allows you to test the exported and reloaded model and confirm that its behavior matches the original version. This step is essential for verifying consistent performance after deployment. After loading the saved model, we run it again on the same sample input used earlier. This checks that the reloaded model produces the same output as before it was saved. Confirming this consistency shows that the model's state was correctly preserved. It also helps ensure the model will behave reliably when moved between different environments for deployment. The code first checks whether the loaded model's output is a dictionary, which can happen with TensorFlow saved model exports. If it is a dictionary, it then takes the first value from that dictionary, since the default output is usually stored there. This step converts the model's output into a consistent format. As a result, the processed output can be reliably compared with the output from the original model. We use a numerical comparison function from NumPy to check that the outputs of the original model and the reloaded model are effectively the same. This function tests whether the two result arrays match element by element within a small allowed difference. We set this tolerance to 1 times 10 to the negative 6 to permit tiny numerical changes that can happen during saving and loading. If the arrays are still considered close under this tolerance, we can be confident that the model behaves consistently after export and reload. The code takes the output from the loaded model, converts it to a NumPy array, and flattens it into a simple one-dimensional form. This makes it easier to directly compare the loaded model's prediction with the original model's output. By checking that these flattened outputs match, we can confirm that the model behaves the same way after being saved and reloaded. The code prints a message to confirm that the outputs from the original model and the reloaded model still match after saving and loading. It converts the comparison to a simple true or false value, where true means the outputs are close enough within a small numeric tolerance. This acts as a final check that the model persistence process worked correctly and that the model's behavior remains consistent. This script shows how to save and reload a simple TensorFlow model using the saved model format. It builds a small neural network, trains it on a tiny dataset with fixed random seeds for deterministic behavior, and records the model's prediction on a sample input. The trained model is then saved to a directory and later reloaded to mimic deployment. After reloading, the script runs the same sample input again and compares the new prediction to the original one. If the two outputs match within a small tolerance, it confirms that the model was successfully persisted and that its predictions remain consistent before and after saving. Model validation checks. Output consistency checks. When you export a model for deployment, you must verify that the exported version produces the same outputs as the original for the same inputs. This means running them side by side on sample data and comparing their predictions, such as labels and probabilities for an image classifier or token scores and generated text for a language model. The goal is to ensure both the overall decisions and the underlying numerical values match within an acceptable tolerance. Treating this as a formal validation step helps prevent subtle errors from appearing once the model is in production. To check that a model behaves the same after export, use a diverse set of test inputs that reflect real-world scenarios and edge cases. For example, a medical imaging model should be tested with scans from different devices and conditions, and a financial model should be tested on both calm and volatile market periods. Run both the original and exported models on these inputs and compare their outputs. Small numerical differences are normal, but large discrepancies may signal that the export process has changed the model's behavior and need further investigation. When checking output consistency between an original model and its exported version, you need both numerical checks and domain knowledge. In high-stakes areas like medical diagnosis, even very small differences may be unacceptable, so outputs must match almost exactly. In lower-risk areas like ad placement, small numerical variations can be allowed if key performance metrics stay stable. You should also examine individual cases with large discrepancies, since they can reveal specific export issues. By combining quantitative comparisons with a qualitative review of these outliers, you can confirm the exported model preserves the original's performance and make any needed adjustments before deployment. Python code output consistency checks. This script shows how to check that a TensorFlow model gives consistent outputs before and after it is exported. It compares the predictions from the original model with those from the saved version. The goal is to provide a simple, beginner-friendly way to validate that the export process did not change the model's behavior. A line that begins with an exclamation mark is a shell command used to install TensorFlow, not regular Python code. It is typically run in environments like Jupyter Notebooks to make sure TensorFlow is available before running the rest of the script. TensorFlow is a widely used library for machine learning and deep learning, so installing it first ensures that all required dependencies are set up correctly. We begin by importing a few standard libraries that the script relies on. The operating system library lets us work with files, folders, and other system resources. The random library provides tools for generating random numbers, which we will later control using fixed seeds. Finally, the numerical computing library NumPy allows us to handle arrays and perform efficient mathematical operations throughout the script. We begin by importing TensorFlow, a powerful library used for machine learning and deep learning. Along with it, we use Keras, a high-level interface that is part of TensorFlow. Keras makes it easier to build and train neural networks, while still relying on TensorFlow's strong underlying capabilities. This combination gives us both robust performance and a more intuitive way to create models. We begin by printing the current TensorFlow version to confirm which release is being used. This helps us check compatibility and know what features and behaviors to expect, since different versions can work differently. By displaying the version at the start, we quickly verify that our environment matches what we need for the rest of the work. We begin by setting a fixed seed value so that any random operations in our code produce the same results every time it runs. This is important for reproducibility, which helps when debugging or comparing different runs. In this case, we set the seed for Python's built-in random module to the value 42. Doing so ensures that all random numbers generated by this module remain consistent across executions. We set the random seed in NumPy so that any random numbers it generates are always the same each time the code runs. This makes the results reproducible, which is important for debugging and checking that our work is correct. By fixing the random seed, we can reliably repeat experiments and verify that changes in output are due to code changes, not random variation. We set the random seed in TensorFlow so that any operations involving randomness, such as initializing neural network weights, give the same results every time we run the code. This makes our experiments reproducible and ensures that we can reliably repeat them. It also helps us debug problems more effectively, because we know that the behavior will not change from one run to the next. We begin by loading the MNIST dataset using a Keras utility, which provides a large collection of handwritten digit images commonly used to train image processing models. This loading stack returns two sets of data, one for training and one for testing. The training set includes the images and their corresponding digit labels, which we use to teach and validate our model. In this context, we focus only on the training data and ignore the separate test set. We select the first 2,000 images from the training dataset to form a smaller subset. This reduced set lets us train the model more quickly, while still using enough examples to learn useful patterns. As a result, we can speed up experimentation without completely sacrificing the quality of the model. In this step, we select a subset of the training labels that matches the subset of images chosen earlier. Specifically, we take the first 2,000 labels from the original training set. This ensures that each selected image has a corresponding label. Maintaining this one-to-one alignment between inputs and labels is essential for correct model training. The code converts the training images to floating point numbers and scales their pixel values so they fall between 0 and 1. To prepare image data for a convolutional neural network, we need to add a channel dimension to the training images. The images start as two-dimensional arrays for height and width, but convolutional layers expect three-dimensional input that also includes channels. By expanding the data to include this extra dimension, we put the images into the correct shape for the model. This step is essential so the convolutional operations can run properly on the input data. Before building the model, The code first checks that the training images have the correct shape. It verifies that each image is 28 pixels high, 28 pixels wide, and has a single channel, as expected for grayscale data. This validation step is important because the neural network's input layer is designed for data in exactly this format. Ensuring the dimensions match helps prevent errors during training and keeps the model pipeline consistent. We build a simple sequential model in Keras for grayscale images of size 28 by 28 pixels. It starts with a two-dimensional convolutional layer with 8 filters of size 3 by 3, using a ReLU activation to extract features, followed by a max pooling layer that downsamples the feature maps by taking the maximum value in each 2 by 2 region. The pooled feature maps are then flattened into a one-dimensional vector and passed to a dense layer with 32 units and ReLU activation to learn higher-level patterns. Finally, a dense output layer with 10 units and a softmax activation produces class probabilities for 10 possible categories, making the model suitable for tasks like digit recognition on the MNIST dataset. The model is compiled using standard settings to prepare it for training. It uses the Atom optimizer, which is efficient and adapts well during neural network training. The loss function is sparse categorical cross-entropy, appropriate for multi-class classification when labels are given as integers. Accuracy is included as a metric, so we can monitor how many predictions are correct during training and evaluation. The model is trained using the Keras fit method, which takes the small training dataset and its labels as input. Training runs for 2 epochs, so the model goes through the entire dataset twice. A batch size of 64 is used, meaning the model updates its weights after processing 64 samples at a time. The verbose setting is turned off, so the training completes without showing progress messages. We create a small validation set by taking a slice of the training data from around the 100th example. This subset is used to check how well the model's predictions match the expected outputs. By validating on this slice, we can confirm that the original model and the exported model behave consistently. The code verifies that the validation batch contains exactly 10 samples. This check confirms that the batch size matches what is expected before any further processing. Ensuring the correct batch size helps maintain consistency in the workflow. It also makes debugging easier if something goes wrong later in the process. We now use the trained model to make predictions on a batch of validation data. To do this, we call the model's prediction function, which processes the inputs and returns the corresponding predicted outputs. During this step, we disable extra logging so that no additional information is printed. This keeps the prediction process quiet and focused solely on producing the results. The code defines a directory where the trained model will be saved, using a folder named nn.Export demo.Keras. This folder stores the model in the saved model format, which is the standard export format for TensorFlow models. Saving the model this way makes it easy to load later, reuse the training results, and deploy the model in different environments. The code first checks whether the export directory already exists using TensorFlow's input and output tools, and if it does, the directory is completely removed. This clears out any previous model exports so they do not interfere with saving the new model. By starting with an empty directory, it helps avoid conflicts or errors and keeps the workspace clean for the next export operation. This step saves the trained TensorFlow model to a chosen directory so it can be reused later. The model is stored without the optimizer to keep the file smaller, and because the optimizer state is not needed when making predictions. Saving the model in this way is essential for deploying it in production, where it can be loaded and used directly for inference. We load the exported model from disk using the keras load model function, so we can reuse it without retraining. This retrieves the previously saved model and makes it available for new predictions or evaluations. By loading it from the specified directory, we can directly compare its outputs with those of the original model and verify that they behave consistently. We run the exported model on the same validation data to generate predictions and compare them with those from the original model. This comparison step is essential to confirm that the exported version behaves the same as the original. The predictions are generated quietly without showing progress messages, so the output remains clean and focused only on the final results. The code verifies that the output shape of the original model is exactly the same as the output shape of the exported model. By comparing these dimensions, it checks that both models produce predictions with the same structure. This is a key step to confirm that the export process has correctly preserved how the model is organized and how it behaves. The code compares the predictions from the original model with those from the exported model by computing the absolute difference between their outputs. It uses a numerical library to take the absolute value of the element-wise differences. This calculation shows how closely the exported model matches the original. It is an important step to verify that the exported model reproduces the same prediction behavior. The code finds the largest difference between the original and exported model predictions by taking the maximum of the absolute differences across all outputs. This value represents the greatest deviation between the two sets of predictions. It is used to check how consistent the model's outputs remain after export and to assess whether the exported model is behaving as expected. The code computes the average difference between the original and exported model predictions by taking the mean of their absolute differences. This single value shows how much the outputs deviate from each other on average. Converting the result to a standard floating point number makes it easier to use in further analysis or comparison. We set a small tolerance threshold of 1 × 10⁻⁵ to compare the outputs of the original and exported models. This value defines how much difference between their predictions is still considered negligible. If the differences stay below this threshold, we treat the models as consistent. In this way, the threshold provides a clear criterion for deciding whether the exported model matches the original closely enough. We are checking whether the difference between the outputs of the original model and the exported model stays within an acceptable range. To do this, we compare the maximum difference to a predefined tolerance level. If the maximum difference is less than or equal to this tolerance, we mark the outputs as consistent. This validation step is important to confirm that the model behaves the same after it has been exported. The code calculates and prints the largest difference between the outputs of the original model and the exported model. This value shows how much the predictions can vary after export. By checking this maximum difference, we can verify whether the exported model is consistent with the original and ensure that its behavior has not changed in an unacceptable way. The code calculates and prints the mean difference between the outputs of the original model and the exported model. This value is the average of the absolute differences across all predictions. It shows how closely the two models agree and serves as an important metric for checking the model's consistency after export. The code prints the tolerance threshold used to compare the outputs of the original model and the exported model. This threshold sets how much difference between their predictions is acceptable. By checking that the differences stay within this range, it helps confirm that the two models behave consistently. The code checks whether the outputs from the original model and the exported model match closely enough by comparing their maximum difference to a set tolerance. It uses a Boolean value to indicate if this difference is less than or equal to the allowed threshold. The result is then printed to confirm whether the exported model's predictions remain consistent with the original model. This script checks that a TensorFlow model behaves the same before and after being exported. It trains a simple convolutional neural network on a small subset of the MNIST dataset, then records the model's predictions on a selected batch of inputs. The model is saved in the standard export format, reloaded from disk, and used to make predictions on the same inputs again. The script compares the shapes of the outputs and measures the absolute differences between the original and exported predictions, computing the maximum and average difference. It then checks these values against a predefined tolerance and reports whether the exported model's outputs are consistent with the original, confirming the integrity of the export process. Shape and dtype checks. When validating an exported model, always confirm that the shapes and data types of its inputs and outputs match the original design. Shapes describe the tensor dimensions, such as batch size or sequence length, and data types describe how values are stored, like 32-bit or 16-bit floating point. Even if the numerical values look correct, mismatched shapes or types can cause subtle bugs or complete failures, such as extra dimensions breaking a recommendation system, or precision changes destabilizing a vision model. Consistently checking these properties helps ensure reliable deployment and further compilation of the model. When validating an exported model, you should carefully check that the shapes and data types of inputs and outputs match what your serving environment expects. This includes both the model's external interfaces and important internal points. If these do not align, a speech model might break because of incorrect sequence lengths, or a financial model might lose precision if outputs change from floating point to integers. By running the same test inputs through both the original and exported models and comparing the results, you can detect these mismatches early and avoid failures in production. When validating exported models, pay close attention to how shape and data type constraints interact with dynamic behavior and optimizations. Modern models often use dynamic batch sizes and variable sequence lengths, so the exported version must correctly handle all intended input shapes, not just a few fixed examples. For instance, a chatbot should work for both short and long messages, and any mixed precision changes must not break assumptions about data types. Treat these shape and data type checks as ongoing responsibilities to keep model behavior consistent as the model and its environment change over time. Python code, shape, and dtype checks. This script demonstrates basic checks of tensor shapes and data types when comparing models. It uses TensorFlow to simulate both the original and exported versions of a model. The main goal is to compare their outputs and ensure they match. This helps verify that the exported model is safe and reliable to use in deployment. This line tells you to install TensorFlow version 2.20 if it is not already on your system. Using this exact version is important because the rest of the script depends on its specific features and behavior. It is a precaution to prevent errors or unexpected results that could occur with a different TensorFlow version. We begin by importing 3 key libraries that the script needs. The operating system library lets the program interact with files and environment settings. The random library provides tools for generating random values and making random choices. The numerical computing library, NumPy, supports efficient work with arrays and mathematical operations. Together, these imports prepare the script to manage data structures, control randomness, and perform its core tasks reliably. We start by importing TensorFlow, a major library used for machine learning and deep learning. This gives us access to its tools for building and running models. We then print the TensorFlow version in use so we know exactly which features and syntax are available, since different versions can behave differently. We begin by setting a seed value of 7 so that all random operations are repeatable each time the script runs. We set this seed for Python's random library, for NumPy's random number generator, and for TensorFlow's random number generator. This makes any random numbers or random behavior, such as neural network weight initialization, occur in the same way on every run. By doing this, we ensure deterministic behavior, which is important for debugging and verifying results. We define a simple neural network using the Keras sequential interface in TensorFlow for demonstration. The model takes input data with 4 features, using 32-bit floating point values. After the input, it has a dense layer with 3 neurons that uses the ReLU activation function, which sets negative outputs to 0 and introduces nonlinearity. This basic feed-forward network is then ready to be trained or used for making predictions. To prepare the model for use, we first create a small dummy input tensor of zeros with the required shape and data type, such as 1x4 with 32-bit floating point values. We then pass this dummy input through the original model once. Running this initial batch builds and initializes the model's internal structures. After this step, the model is fully set up and ready for further operations. We create a simple exported model by cloning the original model with TensorFlow's clone model function, which copies the architecture but not the learned weights. This gives us a clean version of the model structure that is separate from the trained model. We then pass a dummy input through the exported model to build it and confirm that it runs correctly. Once this check succeeds, the exported model is ready to be compared with the original model. We use a helper function called runModelSafely to execute a model only after checking that the input has the correct shape. It first confirms that the input batch is a 2-dimensional tensor, and if not, it raises an error saying the batch must have rank 2. It then checks that the second dimension of this batch is exactly 4, and raises another error if this size is different. When both conditions are satisfied, the function runs the model on the batch and returns the output. This validation step helps avoid runtime errors by ensuring the input shape matches what the model expects before it is executed. We create a small batch of test inputs using TensorFlow's constant function containing 2 sets of 4 floating point numbers. The first set is 1, 2, 3, and 4, and the second set is 0.5, 0, -1, and 2. These values serve as representative examples to test the models. They help confirm that the models correctly handle typical input shapes and floating point data types. We first run the original model on the input data using a safety wrapper that checks the input has the correct shape and types. Then, we run the exported model on the same data using that same safe execution process. By comparing the outputs produced under identical validated conditions, we can confirm that the exported model behaves consistently with the original. The code prints the shape and data type of the input tensor to quickly verify that the data is structured correctly before it is passed to the models. Checking the shape confirms that the input has the expected dimensions, and checking the data type confirms that the values use the correct format, in this case, a floating point type. This simple step is important for debugging and for making sure the input satisfies the model's requirements. We check the shape and data type of the original model's output to verify that it has the structure we expect. This simple inspection confirms that the model is handling inputs correctly and returning results in the right format. By validating these attributes, we can be more confident that the model's processing pipeline is working as intended. We are validating the exported model by examining its output. First, we check the shape of the output to understand the dimensions of the data it produces. Next, we check the data type to see what kind of values it generates, such as floating point numbers. Together, these checks confirm that the exported model's outputs are structured and typed as expected, consistent with the original model's behavior. The code compares the outputs of the original and exported models to ensure they are compatible. It first checks that their output shapes match, confirming that both models produce results with the same dimensions. It then verifies that the data types of these outputs are the same. Matching shapes and data types help ensure consistent behavior and prevent unexpected errors in later use. We begin by printing a summary to confirm that the original and exported models are consistent. First, we compare the shapes of their outputs to ensure the models produce results with the same dimensions. Then, we check that the data types of the outputs match, showing that both models handle data in the same way. These checks are essential to verify that the exported model behaves like the original and can be deployed reliably. To compare the original and exported models, we measure how different their outputs are. We do this by taking the absolute difference between the two outputs and then finding the largest of these differences. That maximum value is converted to a standard Python number and printed. This tells us how closely the exported model matches the original and helps verify that it behaves consistently and reliably in deployment. This script shows how to check that a TensorFlow model and its exported copy produce consistent results. It first fixes the random environment so the model behaves the same every time it runs, then defines a simple neural network and creates a duplicate to represent the exported version. Both models are given the same small batch of inputs, and their input and output shapes and data types are compared. The script also measures the maximum absolute difference between the two sets of outputs to confirm numerical agreement. The printed results verify the TensorFlow version and report whether the models match in shape, type, and values, which is important for validating model integrity before deployment. Debugging export failures. When an export fails or a model behaves unexpectedly, treat it as a structured debugging problem. Focus first on the error messages during export and execution, and relate them to the model's structure and data flow. Many issues come from operations or control flows that the exporter cannot handle, such as data-dependent branching or unsupported layers, which may cause a model to work for some inputs but fail for others. Identify exactly where this happens so you can decide whether to refactor the model, change the inputs, or adjust the export settings to achieve a reliable deployment. To debug an exported model, start by comparing it with the original model using very simple inputs. Reproduce the failure with minimal examples, such as a single batch or synthetic data, to remove unnecessary complexity. When you see differences, record the inputs and outputs at each stage of processing to locate where they first appear. In areas like computer vision, problems may only show up for certain image sizes or metadata, which can reveal hidden assumptions. By changing one factor at a time, such as batch size or padding, you can pinpoint where the model's behavior is too dynamic to export reliably. Once you identify the source of export problems, adjust the model or export process so the exported program is valid and reliable. This often means replacing problematic constructs with export-friendly ones, such as using tensor operations instead of Python loops or avoiding data-dependent changes to tensor shapes. For example, you might refactor a model that builds layers dynamically into one with a fixed maximum length that uses masking, so the computation graph stays stable. After each change, re-export the model and run validation checks to confirm its accuracy and behavior are preserved. Repeating this cycle of analysis, refactoring, and validation improves the robustness and transparency of models in production. Python code. Debugging export failures. This script is designed to help debug export failures by simulating the export process and comparing how models behave. It focuses on running simple checks that highlight differences or problems during export. The script also prints clear, readable messages, so it is easy to understand what went wrong and where. Overall, it provides a straightforward way to diagnose and interpret export issues. In this setup, TensorFlow is already available, so you do not need to install it yourself. The script relies only on TensorFlow and the Python standard library, which keeps the environment simple and free of extra dependencies. This makes it easier to concentrate on the core functionality of the code without dealing with additional installation or configuration steps. We begin by importing a few key tools needed for our demonstration. The operating system module lets us interact with the system environment. The random module helps generate random numbers, which we can control for reproducible results. We then use the numerical computing library NumPy to work with arrays and random values efficiently. Finally, we import TensorFlow, the deep learning framework we will use to build and train our neural network models. We set a seed value, such as 7, so that all random operations in our code give the same results every time, which is important for testing and debugging. We first set the seed for the standard random module, then for NumPy's random number generator, and finally, for TensorFlow's random number generator. Doing this makes all randomness in these libraries deterministic, ensuring our experiments are reproducible and easier to analyze. We begin by printing the TensorFlow version being used because this information is important for debugging and checking compatibility. Knowing the exact version helps you confirm that your code matches the expected environment and works correctly with other libraries. It also makes it easier to track down issues that may only appear in certain versions. In short, displaying the TensorFlow version provides essential context for understanding and troubleshooting the program's behavior. We define a custom neural network class called Dynamic Branch Model by inheriting from the TensorFlow Keras model base class. In the constructor, we first call the parent initializer to set up the model correctly. We then create two dense layers, one called the small dense layer and one called the large dense layer, each producing two outputs. These layers form separate branches that can process the same input in different ways, allowing the model to handle dynamic conditions during execution. In this method, we first compute the mean of the input tensor along its last axis, while keeping the original shape. We then use this mean to form a condition that checks whether it is greater than 0. Next, the input is passed through two separate dense layers, one smaller and one larger. Finally, we use a conditional selection operation to choose between the outputs of these two branches. If the mean is greater than 0, we take the output from the larger branch. Otherwise, we use the output from the smaller branch. Exploited Program Wrapper is a class that serves as a simple wrapper around an existing model, imitating how an exported program would behave. During initialization, it receives the original model and stores it as an internal attribute. This design lets the wrapper reuse all of the model's capabilities while making it possible to add extra behavior or restrictions that apply specifically in the exported setting. This function is used when the exported program is called like a normal function. It first checks that the last dimension of the input has size 3, which is a required input shape for the exported program. If this condition is not met, it raises a value error that explains what shape is expected. If the input shape is correct, it calls the original model with the given inputs, makes sure the model is not in training mode, and returns the result. This design enforces the input shape constraint and keeps the behavior consistent between the original and exported models. We begin by creating an instance of the dynamic branch model, a custom TensorFlow model built to handle inputs with dynamic branching logic. To initialize it, We pass in a simple dummy input made of zeros with 1 row and 3 columns, which triggers the model to build its internal structure and allocate resources. After this initialization, we wrap the model in an exported program wrapper, which simulates the behavior of an exported model. This wrapper enforces specific input shapes and provides a consistent interface for testing and comparison. We use a helper function to compare the outputs of the original model and the exported model. It takes some inputs and a short description, then runs the original model with training turned off and saves its output. It runs the exported program on the same inputs and saves that output as well. The function then computes the largest absolute difference between the two outputs using TensorFlow operations and converts this value to a regular number. Finally, it prints the description together with this maximum difference, so we can see how closely the exported model matches the original. We begin by creating a TensorFlow constant that serves as a valid input tensor, shaped as a 1x3 matrix with specific floating point values to match the exported program's expected input. We then print its shape to confirm it meets the required dimensions. Using this confirmed input, we call a helper function that compares the outputs of the original model and the exported program. This function reports the maximum difference between their outputs, allowing us to verify that both models behave consistently for the valid input. We define a TensorFlow constant called invalid input as a two-dimensional array with 1 row containing the floating point values 0.1, -0.2, and 0.3. This input is deliberately chosen to cause a failure when it is passed to the exported program. We then print its shape to verify that its dimensions match the program's expected input shape, even though using it will intentionally lead to an error in later steps. We deliberately run the exported program with an input that does not meet its requirements in order to trigger an error. This call is placed inside a try block, and because the input has the wrong shape, the program raises a value error. The except block then catches this error and prints a message saying that an export style error was caught, along with the specific error details. This shows both that the exported program enforces its input constraints and that such errors can be handled cleanly using structured error handling. This example shows that the original model can still run with invalid input, even if the resulting output shapes are not what we expect. The same input causes an error in the export inversion, which strictly enforces input shape requirements. In contrast, the original model is more flexible and accepts the mismatched input. The code then prints the output shape from the original model to reveal how it differs due to this input shape mismatch. This script shows how to debug export failures in a TensorFlow model that uses dynamic branching. It defines a simple model whose output depends on the mean of its inputs, then wraps it in an exported program that enforces a strict input shape where the last dimension must be 3. The script compares outputs from the original and exported versions on a valid input and reports their maximum difference. It then runs the exported model on an invalid input, which raises a value error due to the shape mismatch, while the original model still accepts and processes that same input. This contrast illustrates that shape constraints can be introduced by the export wrapper and may not reflect the behavior of the underlying model, highlighting a potential pitfall when exporting models with dynamic behavior. In this lecture, you learn to describe the purpose and capabilities of torch export in PyTorch 2.10.0, export a trained nn.Module to an exported program suitable for deployment or further compilation, and inspect and validate exported models to ensure they produce consistent outputs with the original model. In the next lecture, Lecture B, we will go over serving models. Thank you for your attention. See you all in the next lecture.